Good afternoon, Physics 30s. Mr. Thompson here. We're looking on page 50 of our workbook on electromagnetism. It starts off kind of like this. Magnetism and electricity are similar in many ways. So one of them is called the bipolar nature. There's only two possible natures. Just like in positive and negative charges are the only two types. The other one, of course, is the fact that there's only a north and a south pole. There's no other type of pole. Distant forces. Forces can repel or attract. As distance increases, force decreases. And so the idea of repelling or attracting is common for magnetism as well as electrostatics, really. And so number three is field theory. The fields produced look very similar. So positive's kind of like a north pole and negative's kind of like a south pole. They're not interchangeable, but you can think of it like that in a way. Induction, they both can affect some neutral objects from a distance. Just like a charged object attracts a neutral one, the idea of a north or a south pole of a magnet attracting some ferromagnetic material. Oersted in 1820 discovered accidentally that they're in fact highly related. He found that an electric current produces a magnetic field. And so what we do is we look at a magnetic field about straight wires. So if a current carrying wire, of course with electron current moving to the left, there is a magnetic field that's generated that circles the wire. Okay? And so we call that rule number one. It's the magnetic field around a straight current. You can call it the first hand rule for conductors, is a common term for it. The thumb points in the direction of the current, and the curled fingers is the direction of the magnetic field. So if electron flow, that means flow of negative charge, then what we do is we use our left hand. If it's the flow of positive charge, you can use your right hand. And so to simulate that idea, right, you can use your pencil, set it on your page, and of course use your left hand. And if the current is going to the left, okay, like my thumb is pointing, then my hand curls around showing the magnetic field. If, of course, the wire was turned and it was pointing straight up at you, then the magnetic field would circle the wire, okay? In this fashion, we call it clockwise, okay, as the current's pointing straight up. Thumbs up, everyone, okay? When we do magnetism, it's very important for us to be able to talk about three dimensions. And so we have vectors that are into the page and out of the page indicated in this way. Into the page, we have a little X with a circle, or just simply an X, and then out of the page is a dot, generally with a circle around it. Here's an example for you. Sketch the magnetic field around the wire. Well, I can see here, if this is negative and this is positive, then electrons, of course, will be moving in this direction, from negative to positive. Okay? If negative electrons are moving in that fashion, then what I can do is I can point my thumb in the direction, okay, of the electron motion and then grasp, okay, around, circling the actual wire itself. Now, in the textbook, it's called the wire grasp rule. I call it the first rule, hand rule for conductors. And in the case of this, if you think about it, here's your pencil. Wrapping your hand around, the magnetic field goes down on the top of the wire and then curls back around and comes up on the bottom of the wire. Okay? So we draw it like this. This would be your magnetic field into the page here and then out of the page here. Like I said, sometimes you're going to see that they're going to want to identify these X's and the dots by putting circles around them. Okay? Now, if we take a look at the next problem, this is, of course, the direction of the magnetic field at location A. Notice this, a P positive, that's a proton that's moving. So in this case, I'm not going to be using my left hand, I'm going to be using my right hand. And so what we do is we show the direction of motion of the charge with our thumb, and our hand circles around. So, same idea with the pencil. You can take your pencil, point it downwards with the tip pointing downwards, and then circle your right hand around it. Okay? The charge is moving down, thumb, and my hand curls around, showing that, of course, at point A, it should be an X. Okay? Next page. By the way, I'm posting a little video which shows a little bit about how to use that hand rule. I have a power supply and a few wires coming from it, a light bulb lit up, and I have small little compasses. Okay? If we look, of course, at solenoids, this is like a coil of wires. And so the magnetic field of a solenoid is the sum of the magnetic fields of all its loops. And so what is a solenoid? It's just a coil of wires. Okay? which has many loops or turns. As a result, the field inside the coil is very strong and uniform. The field outside the solenoid is similar to a bar magnet. And we get rule number 2. It's the rule for solenoids. We can call it the hand rule, second hand rule for coils. That's how I like to term it. We put the fingers curling around in the direction of the current around the solenoid, and in other words, the turns or the windings of wire, and the thumb points towards the north pole of the solenoid. It says for negative charge, use your left hand. And so you notice, what do you do here? Well, you notice the positive charge is here, negative is here, and so electrons are moving upwards on all of these parts, all these bits of wire. Okay? That allows you to figure out how to wrap your hand around, because what you need to do is you need to wrap your hand around, okay, in the direction that the current's going on the front. My thumb points towards the north pole of the solenoid, it being on the right side there. Okay? It says here the thumb also represents the direction of the magnetic field inside the solenoid. Okay, so inside the solenoid within it, it would be going in this fashion. Okay, not above it, but inside it. Here's an example. Okay? Predict the poles of the electromagnet and determine the direction that the compass is pointing. Okay, so what we do is we first of all label the polarity of our battery, and then we notice the direction of the electron current. Okay? Now it goes behind, okay, the core there, and then this way, all the way along it. Okay? And then back to the positive end. So this is the direction of electron flow. So what am I going to do? With electron flow, I'll use my left hand. Okay? Left hand for solenoids or for electromagnets. I take my left hand, I put my pencil to simulate that core, I wrap my hand around, okay, showing the direction of the current on the top part, right, above the core, and then my thumb points towards the North Pole. So this would be the North Pole here, this is the South Pole down here, and then the poles for the electromagnet, shown there, the compass now. The compass should have the North Pole pointing away, where this is north and this is south. And then as, of course, it loops around into these loops, like we talked about magnetic fields around bar magnets yesterday, then you see that this should line up very much. That was beautiful. So that the North Pole is pointing in that fashion. Okay? All right, we have a few problems for us to work on. Let's take a break for just a second.